How can a cube smoothly melt into a sphere with a glowing energy halo on its surface? Today, we'll use the Three.js TSL node system to build it, just like assembling Legos. Starting with the TSL morphing file, we will build the morphing and glowing effects step by step. I've prepared a Canvas WebGPU component in advance. This component encapsulates the canvas from R3F, specifies the WebGPU renderer, and includes a built-in default camera, orbit controls, and a dark background. The advantage of this is that we can reuse it in every new project, without having to write this repetitive boilerplate code each time. Alright, let's get back to tslmorphing.jsx. I'll start by generating the basic structure with a functional component template. Now, let's import the Canvas WebGPU component we talked about earlier. It will manage the entire scene for us. Next, I'll create a morphing and moving mesh components. For now, I'll just place a highly subdivided box with a placeholder material inside it. The 128 by 3 subdivisions are to prepare for the morphing effect we'll add later. Let's add this mesh to our scene. With the dev server ready, I'll switch over to the browser. Okay, the code is running correctly, so we now have a minimal runnable version. I'm going to keep the code and the preview side by side, so from now on we can see the immediate results of every step. Okay, first let's set up two routes. MeshRef will handle the mesh's position, and MaterialRef will handle the material. We'll use useMemo to assemble our TSL node graph. For the material, we'll use Mesh Basic Node Material, so we can focus purely on the color and shape, as it's not affected by lighting. Let's start with a basic white color and set the morph progress to 0.35 for now. The animation will take over this evaluator. Now we can get rid of the placeholder material and assign a new TSL material instead. Let's start by defining the vertex positions. NoiseScale will control how dense the noise texture is. Think of it like zooming in or out on a cloud map. Noise strength determines how much that noise will actually affect the deformation. We get the cube's original vertex position using positionLocal. Then, by normalizing that, normalize positionLocal, we get a direction vector that points from the center out to the surface of a sphere. Fractal noise stacked in 3 layers frequency times 2, amplitude times 0.5. Then apply offset and compression to map the result into 0 to 1 range. uProgress is our global progress uniform, but we're going to use our noise to make it jitter a bit. Clamp it between 0 and 1. This is what makes the transition boundary look more like a liquid creeping across the surface. We can now mix the cube's original coordinates with the sphere's direction vector. You can think of this as giving each vertex a slider. When the slider is at 0, it's a cube, and when the slider is at 1, it's a sphere. Finally, we'll pass that result to the position node, and now you can see our shape is in an intermediate state between a cube and a sphere. This line of code passes each vertex's local progress to the fragment shader to control the emissive band. Switch to the fragment stage. Lay down the base color, then layer the energy wave. Use base color as the base. Noise color from modeled highlights. Add fractal noise. Use smoothstep 0.2, 0.8 to widen contrast so the pattern is clearer without overexposing. Mix the base and noise first and plug them into the material. Now a blue-green modeled cube sphere hybrid appears. Glow color sets the emissive band color. WaveWidth controls the band thickness. Recenter the progress around 0.5, take the absolute value, then invert it. Intuition: the closer to the deformation front, the higher the value. Finally, blend the energy wave into the surface color by weight and pass it to color node. A purple energy band now traces the deformation boundary. We put the timing logic into useFrame. Timestamp the shader every frame so the animation runs on its own. Move is the motion duration. Pause is the stop duration. Total makes the animation wrap end to end. P is the deformation progress in 0 to 1. We drive shape and color by adjusting this single knob. First phase, P ramps linearly from 0 to 1. Briefly hold out 1. Return phase is also linear. Add a floor guard to avoid rare edge cases dipping below 0. Clamp keeps P within 0 to 1. This line reduces jitter. Cleaner values make a steadier image. Use the same P for displacement. Attach the ref to mesh. The animation shouldn't be this slow. Let me check what the issue is. Here it should be %, but I wrote slash. Now we see cube to sphere to cube repeating. Now let's tune noiseScale and see what it does. Pull it down to 0.5. The input frequency drops, equivalent to zooming the height map out. You now see broad, smooth transitions, like jelly slowly bulging. Set it to 6.5. The input frequency rises, so neighboring vertices sample more divergent noise. The sphere morph boundary becomes fine and jittery, as if tiny wrinkles took a bite. If it looks too noisy, we go back to 2.5 for a steadier look. Used fractal noise and smoothstep to make the boundary natural, and use noiseScale to pick your preferred grain size. Next time we'll add a click or touch ripple. If this episode helped, please like or subscribe. See you next time.